I just wanted to present some of the ideas that we came up to in our lab on the generation of new titanium alloys targeted for laser powder bed fusion, which is the technique that we use the most in the labs. But of course, some of the considerations can be applied elsewhere with different additive setups. And most of the work that I'm going to present today is actually performed by Zhu, my postdoc in my team. But of course, we are an enthusiastic team, a small team, and we all contribute with different ideas. So for those who don't know CFAM, Center for Additive Manufacturing in Nottingham, well, CFAM is a fairly large group. So it was established in 1992 by Professor Phil Dickens. Back then, he used to be called Rapid Prototyping. And then Phil made a lot of work to establish this new terminology. So transitioning from rapid prototyping into additive manufacturing. So it's a fairly large group. We are based in this building here, lovely building there. We take up the ground floor. And it's about 100 people altogether in the lab. Just to give you an idea of the flavor of the research they were doing, most of the funds that enable our research is actually EPSRC, which is the main UK funding agency for engineering, the equivalent of NSF in the United States. So we consider ourselves as an industrially focused group, but scientifically driven. So we own our machines and we look predominantly at low TRL type of research. So within that, there is kind of my group that looks at materials for LPBF, 5 or 6 PhD students and a postdoc, and myself. So we are kind of a niche within CFAM. If you are interested in learning more about the facilities, you can go online and you can have a virtual tour of the labs. So there is this lovely fly through the lab. You'll be able to see the equipment and have an idea of what we have in the lab. Or otherwise, just contact me, and we are really open and welcome any visits. All right. So the core of the topic of my presentation is, as I said, titanium alloys. And I guess the point and motivation behind this work is that, generally speaking, we are very much stuck with legacy alloys for the most part. But if you actually look at what has been used in the aerospace sector, it's 5 or 6 alloys, and all of them were sort of developed after the 50s with thermomechanical working in mind. Obviously, the processing behind these alloys starts from ingot manufacture and some sort of mechanical working, as I said, rolling or forging. So there are some limitations behind the compositions that you can actually achieve there. So the point is, as the technology progresses through the years, it's only natural to think that there will be some new grades which are actually more suited to the technology that we have now available. So kind of this is the teaser and why we're doing the work that we're doing. So this is the reference microstructure that we all have in mind when you think about titanium alloys for aerospace. This is not achievable, okay? LPBF, you just don't have this deformation step in the middle. Unless you're doing exotic work, it's really, really difficult to achieve this dual microstructure there. Actually, what you tend to get is this sort of microstructure, which tends to be acicular, magnetic, and quite often quite brittle. And of course, you can sort of break that if you like. You can do some sort of post-processing, which are more or less intensive, recover some of the equilibrium microstructure, but there is an intrinsic signature imparted by the process, which is not really difficult to get rid of. So the question is this it? And of course, we had some ideas. So what we thought we ought to be doing was essentially access some of the transformation pathways, which are quite easily accessible in LPBF because of the fast dynamics of the process, this rapid solidification that you have available. And we thought these conditions really open up a design space to create really interesting microstructure. And this shaded area, green shaded area there is the design space in this pseudo binary diagram where we are doing most of the work. Traditional alloys sit somewhere there. We don't really want to be up here for reasons which will become clear very soon. We just want to access that middle sort of region there where things start to get quite interesting. This is quite interesting. One of the reasons is because if you're in that intermediate green region, you start to retain metastable phases, so phases which respond to the external environment. As we saw this morning, Chris presented really exciting work on shaping memory alloys. The concept is quite similar. So you can apply strain and see the microstructure evolving. Not only that, but they respond also to heat treatment. So if you want to nucleate fine particles, well, these phases are quite interesting. And generally, yeah, we just want to have additional deformation mechanisms to break this strength ductility trade-off, which you typically have with alpha plus beta titanium alloys. So funded by the US Army Research Office, we started this project a year ago. And we took Ti-64 as a reference, our benchmark alloy. And we thought, well, what we want to do is achieve basically an alloy which has properties highlighted in this green kind of segments in this spider chart. We want to increase ductility relative to Ti-64. We want to decrease cold crack sensitivity because we know that Ti-64 suffers quite a lot from delamination, cold cracking. And most importantly, we want to decrease costs because otherwise you use these alloys only for safety critical aerospace applications. And sort of in gray, you have some of the ideas, the concepts we have settled on to achieve improvements in the properties highlighted in yellow. So we want to have extra ductility by enabling a thermal phase transformation induced by strain. We just want to suppress solid phase transformations. So this beta to alpha prime type of transformation to decrease stresses in the part. And we want to have a material which comes from inexpensive feedstock, which doesn't really need a lot of post-processing, and a material that prints well because costs are associated to machine time. So you really want to have high processing speed and you want to have strength so that you deposit less volume in the machine. That way you'll be able to drive costs down. And we did most of this work on a ternary alloy, titanium chromium tin. And the reason for that is quite simple because there is some literature on that system. And we thought we could draw some insights from that and apply that in our research. Right, again, this is another background slide, I suppose. Essentially, we want to activate trip and twig in our system. So we want to be somewhere there. We started, we are an additive lab, right? We're not a school of metallurgy, so we are experts in printing. So we started to think, what is the typical thermal cycle that the material will experience? And what do we need to kind of look after for? And we thought, well, the first thing is we need to control what happens, or try to control what happens after the first solidification, right? The first layer of the deposit. So what we want to have is we want to retain metastable beta, right? And we thought maybe some semi-empirical parameters to do that are molybdenum equivalence and Martin-Selick start temperature. So we have some analytical equations for them and that link that composition. So we can do some collect some ideas around that. The second thing we want to do is control the beta stability as a function of thermal cycles. So layer n+1, +2, so on and so forth. And I accept that this is a function of process parameters, right? So, yeah, somehow depending on the thermal inputs. But again, this relates quite a lot on the stability of the beta phase. So you want to have a little bit of stability so that as soon as you're, again, up in temperature, you don't start to precipitate some HCP phase. So having all this in mind, we started to do some calculations, and we started to see that basically you can sort of plot martensitic start temperature versus molybdenum equivalence, and you have this downward trend. But what's most interesting is that it's not just a line, it's a band, right? So for a fixed molybdenum equivalent, you have a range of martensitic start temperatures. And essentially where you want to go is at the bottom of this yellow band. And we started to think, well, if you want to minimize hot cracking for the reasons we know from the previous talk, you want to minimize solidification range. Therefore, you want to keep your beta stabilizers quite low. So you want to have a low molybdenum equivalent as well. So we want to stay kind of on the left-hand side of this chart, but also on the bottom, right? The other thing we want to do is, yeah, we can obviously do a lot of MATLAB calculations and see in this ternary what sort of compositions meets that sort of criteria. The other thing we want to do is, again, as I said before, access this strain transformation, this triple TWIP. So we can access this really nice empirical diagrams, Morenaga's diagrams, and we can see basically we want to be in this red box here. So we want to be in between this TWIP and TRIP boundary lines, because we think most likely we'll be able to excite some of this strain transformation if we fall there. So what we did a lot of powder-free tests in the lab, a lot of art melting buttons. And then on the flat surface of the button, what we did, we put the buttons inside our machines, the printing machines, and we basically surface melt the top flat surface of the buttons to kind of recreate the thermal history that you would have in one layer. But the beautiful thing is that obviously you have this sequential adjacent tracks, which sort of simulate a thermal cycle that you have in the process. And then we studied them. And if you're not careful, you get this sort of decomposition due to the thermal cycle. So at the top, you have a kind of a picture of the microstructure in the bulk of the button, just one solidification event. But obviously, if you raster the laser on top of it, you have, subsequent thermal cycles and precipitation of alpha phase, which is in red. So if you're not careful, you get that. That's what we don't want. A lot more testing. I don't really have time to go in detail, but this is also the range that our experiments showed was most interesting in the ternary that we examined. This is the kind of range of chromium and the range of tin, which we experiment in the machine. And there are many things that need to be taken care of. And scientifically, the role of tin is really, really interesting. Tin has this ability to suppress some deleterious phases in phanium alloys and modulate the activity of TRIP and TWIP. So hopefully we'll be able to publish a paper soon on this. Really, really interesting. At the bottom here is the first composition that we tried, which kind of experiments and calculation showed to be quite interesting. And what we did was we bought elemental powders, we mixed them together, print them in the Renishaw AM400, and then we homogenized the composition doing extensive heat treatments, which obviously we won't do if we had pre-alloy powders. This is just to homogenize this feedstock, which was not homogeneous in the first place. This is the as-built microstructure, which you don't want. A lot of segregation of tin, a lot of segregation of copper and commercially pure tie. We don't want that. This was used just to understand whether the nominal composition, the real composition was quite close to the nominal composition that we had in mind. We saw that a lot of chromium evaporates in the process, so you have to compensate that if you really want to achieve your design composition. And this is what you get after a heat treatment to homogenize the builds. So a lovely beta phase, metastable beta phase, with some unwanted alpha grain boundary, which most likely is due to the fact that we have less chromium than what we thought we would have. But nevertheless, the system is, still in an interesting space. This Morinaga diagram. And this is the proof of the pudding. So basically, we did some tensile tests, and for reference, in light gray, I have as-built Ti64, and all the other curves at the bottoms are just different slight variants around 7.5 chromium, 4.5 tin. After the solution heat treatment and quenching, and what you see is that some nice ductility. Not as much as we wanted to, but still something workable, which gives you some dissipation, some energy absorption capabilities. And again, this is a very cheap system. Why do you get that? Well, because you have a lot of transformation induced. You have a lot of HCP. That comes from your BCC as you apply strain, and there's some evidence of that. So this before testing and after testing, and you see that the microstructure is quite different. And with that, I would like to wrap up the talk. So hopefully, I've showed you that we can exploit rapid solidification to create advantageous chemistries. So in our case, our design procedure has been guided by two parameters predominantly, and then we did a lot of powder-free testing to validate and put things in place. And the preliminary work shows that we can excite this nice trip behavior, and the tin really deserves quite a lot of attention, and really interesting. And with that, I'll thank you for the attention and welcome any questions. Thank you.